up to this point, our conversation about motion has dealt with things that are going in a straight line. Okay, so linear motion either in the horizontal direction or the vertical direction. And we're going to start talking about now 2D motion, so motion in 2 dimensions. So that could be a couple things. So that could be like motion that's occurring on a flat surface in 2 dimensions. Okay, so for example, this ice skater, or something that is flying through the air that has just 2 dimensions. So like a projectile that's launched, and then it has some sort of horizontal, an initial horizontal and vertical velocity, but in the air it's only under the influence of gravity, so it keeps that horizontal velocity, and gravity will accelerate the object. So like for example, a basketball shot, it'll go up and then come down. It's moving in just 2 dimensions, not 3 dimensions. Everything we learn about 2-dimensional, how you handle like a 2-dimensional problem can be just kind of expanded to 3 dimensions by adding that z-axis. Okay, so everything we talk about in 2D can be applied to 3D. We're going to spend most of our time, though, focusing on 2-dimensional motion. Okay, an example of 3-dimensional motion would be these fighter jets. They're moving around in all 3 dimensions. Okay, up, down, left, right, and forward, backwards. Okay, so motion, there's plenty of cases where motion is 2 dimensions, but motion in 3 dimensions is the most common, right? Because we live in 3-dimensional space. Okay, in order to talk about motion in 2 and 3 dimensions, we have to come back to the idea that position, velocity, and acceleration, all these quantities we've been talking about are all vector quantities. Okay, and in 1 dimension we were able to just put a plus or a minus sign, and that was cool. That told us the direction of that vector. In 2 or 3 dimensions, it's a little bit more complicated than that to talk about the direction of a velocity vector, for example. So let's again make the distinction between what is a vector and what is a scalar. So vectors have both a magnitude and direction. So like a position, you could say 5 meters and then locate them behind me. Or if you want to say 5 meters, negative 5 meters, if you've established a reference frame, you need some sort of magnitude and a direction. Okay, or displacement 5 meters to the northeast. 2 meters per second, 20 degrees above horizontal. Okay, so that would be a velocity where something is traveling above the horizontal. Or an example of an acceleration, you can say accelerating to the right. And like I've said, if we're dealing with linear motion, you can just kind of add on a plus or minus sign. But when you're dealing in 2 dimensions, for example, like this velocity, that's 20 degrees above horizontal. Okay, and likely if you're shooting something above horizontal or it's traveling this way, it'll also be under the influence of gravity, and then you get some 2-dimensional motion going on. Okay, on the other hand, scalars only have a magnitude, so your distance, speed, temperature, and mass, you don't need to associate, it really doesn't make sense to associate a direction with them. Like temperature, what would a direction of temperature mean? Okay, also mass, they tell you how much, how big, and how far, just like a vector quantity does. Okay, but the vector adds on that piece of information of in what direction. Okay, vectors, they can be described in terms of their components. Okay, so we're going to switch over. So we've been talking about vectors and kind of mentioning them, but modeling a vector, it's very useful to put an arrow on a coordinate plane. So here an XY coordinate plane, that is what I'm going to use as an example. You could also have like north, south, east, west. Okay, that plane. But if you place an arrow on a coordinate plane, and this is for a 2-dimensional vector, you can describe it in terms of its magnitude. So this would be a velocity vector with a magnitude of 20 meters per second, and also its direction. We can say that velocity vector is is pointed in a direction of 53.1 degrees above the x-axis, above the positive x-axis. So that's one way to describe this vector. But there's actually another way, and this other way is probably what we're going to be using a little bit more in physics class. It can be described by its components. Okay, so we have the x component of this v vector, this vector v, which happens to be a velocity vector. And notice the units of this x component are also velocity, meters per second. Okay, so this is the x velocity is plus 12 meters per second. Okay, and this y velocity is plus 16 meters per second. The reason we're going to be doing this is because two-dimensional motion and three-dimensional motion can actually be analyzed by splitting it up into its component parts. So its horizontal components and its vertical components are independent of each other. So that actually works out really nicely, and all the analysis we learned for linear motion can be applied to two- and three-dimensional motion. Okay, a vector, the magnitude and direction stay the same regardless of the origin, so regardless of where you set your reference frame. Our reference frame up to this point has been pretty much a straight line with a point that says that's the 0 point. There, that's our 0 location, and then our arrow tells us what the positive direction is. Now we're going to have like a coordinate axis that establishes a 0 point for both the x and y. That's our origin, and then a positive x and y direction. Okay, and you'll notice our vector, the components and the magnitude and direction do not change depending on where we place our vector. Okay, so let's say I give you the magnitude and direction of a vector, and here this is an acceleration vector, let's say, for example, and you want to find the components. Okay, this is from trigonometry. You likely learned that the sine of an angle is equal to the opposite over the hypotenuse. So in this case, the opposite is going to be the y component of this vector A, okay, divided by the hypotenuse here is just the magnitude of the vector. So these two lines, they're like absolute value signs, but they're the magnitude of the vector, which means you just take this magnitude. Okay, so 15 here. Okay, so we can solve by rearranging this equation and multiplying both sides by the magnitude of the vector here. We can solve that this y component of this acceleration vector is going to equal 15 times the sine of the angle here. Okay, so 15 times the sine of 36.9, and we get that AY is 9.0. Okay, and if we were putting our units on here, if this really is an acceleration vector, the units would be meters per second squared. Okay. And similarly, we know from trigonometry that the cosine of an angle is the adjacent over the hypotenuse. So in this case, the adjacent side of this triangle would be the x component of this vector. So ax divided by the magnitude of this a vector. Okay, so if we rearrange this again by multiplying by the magnitude of a, we get that this x component of the acceleration vector is equal to 15 times the cosine of the angle, 36.9. And we get that the side length of that triangle, or the x component of this acceleration vector, is equal to 12. Okay, so sine and cosine can help you if you know the magnitude and direction of a vector and you want to know its components. Use your knowledge of sine and cosine to do that. Okay, so there also might be a time when you know the x and y components of a vector, and I ask you, okay, what's the magnitude and direction of that vector? Okay, so we're also going to use knowledge from trigonometry. Pythagorean theorem tells us that the square of both sides, if you add those together, that's going to equal the square of the hypotenuse. So if we rearrange that a little bit, we can find the magnitude of this vector by taking the square root of the x component plus the x component squared plus the y component squared. Take the square root of that, and that'll give us the magnitude of the vector. So here we get the magnitude of b, or the length of that vector, is 11.4. Okay, let's say we wanted to find the direction, right? Because we're not really done. If we know that the magnitude is 11.4, we're still missing some information about that vector. We need to know its direction. Okay, so here tangent is going to be helpful. If you know these two sides, okay, the tangent of this angle right here that you're looking for is going to equal the y component over the x component. Okay, so we can take the inverse tan, arctan of the magnitude of by over the magnitude of bx, or the absolute value there. So if you use the absolute value, this is always going to give you just the angle from the x-axis. Okay, so anyway, if we plug that into our calculator, you'll have like a tan -1 button, or like an arctan. You take the y over the x, you get 15.3 degrees, and that looks reasonable, correct? Okay, and like I noted, this equation will always give you an angle less than 90 measured from the x-axis if you ignore your positive and negative sign. You've learned in math probably other ways to do that. In physics, I like to just like kind of know where I expect this vector to be pointed, and just take a like I know when I plug into here, I'm going to get an angle between 0 and 90, and then I'm kind of responsible of determining exactly which direction that points, but I know it'll be a positive angle from the x-axis that I'm getting. Okay, so here I'm just 15.3 degrees above the positive x-axis is how I would report that. Okay, a couple other things that you can do with vectors. You can add two vectors together, which we are going to be doing quite a bit. So if you're adding two vectors, okay, so let's say we want to add vector A with vector B, okay. So graphically, you line them up like you put the tail of B on the arrow of A, okay, but essentially when you're solving for C here, if you wanted to give the components of C, okay, you basically just have to add the components, the x components of A and B together and the y components of A and B together. Okay, so we take our 12 from A and our 11 from B, so those are the x components of A and B, and I've just drawn them on the x-axis, which looks right for A, but B, I mean, a lot of times you would draw that right here, correct? But I've just bumped it down to the x-axis here, right? You can move vectors around, it doesn't change anything about them. Okay, and then we have our y components. So this side of the y right here is 9, or yeah, this side, or this component, the y component of vector A, is going to be 9, and the y component of vector B is going to be 3. Okay, and I'm just getting these numbers off of this graph. Okay, we'll do some examples in a kind of supplemental video where you have to actually solve for these values, and you just get them by how I explained previously. You can use cosine to find the x and sine to find the y. Okay, anyway, in order to get our x component for C, we just have to add these two together, 12 plus 11. Okay, so our x component of C is 23. Okay, and our y component of C is going to be 12. Okay, so if you break A and B into their x and y components, add the x's together, add the y's together, that gives us our components of C. So let's say instead we wanted to do some subtraction. So we wanted to subtract vector B from A. Okay, so this is going to be the same vector B that we had up here, but now instead of adding it to A, we are going to subtract it from A. So you'll see when we subtract it from A, it's going to be pointed in the opposite direction. Okay, so we've taken each component and turned it negative. Okay, so D is going to be our resultant vector if we take A minus B. So how will we actually solve for the components of D? Well, we need to subtract, we need to take AX and subtract B from it. Okay, so that's visually what it looks like when you subtract these components, is this vector actually kind of flips around, and then you add like the negative of each component to A. Okay, so we take AX minus BX. Okay, so that was 12, AX was 12, minus BX is 11. Okay, so that's how we find the X component of D, and that makes sense. It's going to be really small right in here. It's going to be 1. Okay, and then AY, and now our B has flipped. We're going to subtract BY, so 9 minus 3. So instead of taking 9 plus 3, we take 9 minus 3 over here. And instead of 12 plus 11, we take 12 minus 11. Okay, pretty straightforward. Visually, it means you're kind of like flipping this vector around. So instead of it pointing this direction, you've taken each of its components and made them negative. Okay, so our result, we get the x component is 1 and the y component is 6. And right now I haven't been including units, but there would be, in physics, there's always units associated with these values. Okay, the last thing we're gonna talk about is multiplying a vector by a scalar. So let's say we had our vector A, our trusty vector A that we've been working with, and we wanted to multiply it by some constant n. Okay, well what you need to do is you just need to multiply each of these components by n. Okay, so let's say our n was negative 0.5. Okay, so we're going to take 12 times negative 0.5 and we get an x component for our e vector of negative 6. Okay, and then we need to take this 9 multiplied by negative 0.5 and we get negative 4.5. So that's our y component of this resultant vector e that we get when we take negative 0.5 times vector A. So our resultant vector e is going to be right here, and it has components of negative 6 in the x direction and negative 4.5 in the y. Okay, and then of course we could go from our components, we could get our magnitude by Pythagorean theorem for e, and we could get our direction right here from the x-axis using our inverse tan of 4.5 divided by 6. Okay. Okay, like I've said, that understanding linear motion is going to help us quantify motion in 2 dimensions, or it can be extended and also in 3 dimensions. And that's because because these are all vector quantities that we're dealing with, we can split them into their components and then just look at each dimension like it's a linear problem and then come back and put them back together at the end. So it's, again, a 2-dimensional problem. So working through problems, you'll see basically we'll have an inventory list of our x variables and an inventory list of our y variables. Solve those kind of separately. The time connects them, but solve those separately, and then at the end kind of combine that back into a 2-dimensional vector. Okay, so each dimension is able to be treated as a separate 1D linear motion problem.